Okay, so this is a tutorial on gas laws. So we're working on some problems here. Somebody do that calculation for me. Say that the volume was 1.5, actually let's do this, 1,500 milliliters. And they want to know how many moles is there. Okay? They won't tell you the constant, you need to know it. So what is the constant? Because we look at this and say, oh yeah, it's permanent, PV equals nRT. But we need to know what the constant R is.
So you're solving for N and R?
Just N. We have, R is always constant, so it's a constant. So this is a number that's constant. The unit that's constant is this. Now that constant, the unit on the constant tells me what everything else has to be in. So pressure has to be in atmospheres, and I'm in torrs. So I need to change that, and I picked a constant here, so 1 atmosphere. It actually is 1 atmosphere. Okay.
So in Bergner, is it usually you're going to have to convert for that?
You're going to have to convert something. They've got to be in these units. That's the only one that has to have more than just Kelvin for the units. Yes.
When R has like Celsius in the labeling, do you use Celsius in the equation then?
R won't have Celsius, it has Kelvin.
On a couple, yeah, but on a couple of the saplings, it actually has C there instead.
If it has a C, then you would use a C, but it shouldn't have a C. They must have an issue because it's supposed to be in Kelvin.
Could it ever be like they have you do torr times liters on top, or is it always going to be atmospheres?
You could change your R if you wanted to by figuring out what it would be, but it's a lot easier to change the things here and just memorize this constant and keep them all that way. Okay, so the other thing we need is liters, so we're going to change milliliters to liters. So there's 1,000 milliliters in 1 liter, so 1.5 liters. Did anybody add that other one up?
The 736?
Yeah, this. Should be like 110, 109. Should be like 109.15? 309. Yeah, 309. 309.15 Kelvin. Okay, so now what we need to do, I like to rearrange it first. You don't have to. You can put in everything you've got right now and then solve for N. It's up to you. Okay, how do you want to solve it? Do you have a druthers? Do you want to plug the numbers in, or do you want to solve first and then plug those? It's just how you like to do math. So let's just plug in and see that way first then. Okay, so we're going to take P, which is 1 atmosphere, times V, which is 1.5 liters, equals N, which we don't know, times R, 0.0821 atmospheres times liters divided by mole Kelvin, times by T, which is 309.15 Kelvin. Okay, so then you times both sides, and here you'd end up with 1.5 atmospheres times liters equals N. And over here, K would cancel. So times that through real quick and get a number. We've got the units ATM times liters divided by mole. Let's scroll this up a little bit.
Oh, wait, now we're dividing by atmosphere times liter.
I'm just taking the units. All I've done is just crossed out Kelvin right here.
So
I still got to keep my units.
That's just like telling you what you can have in the equation. You don't really use it.
I've got to keep track of it because I should end up with moles at the end. If I don't, then I screwed up.
Okay.
So it's a good way to keep that under control. So if I take a calculator here and we go 0.0821, that should be a 1 there, times 309.15. I get on this side 25.38, and then I would divide both sides by 25.38 atmospheres times liters divided by mole. Over here, everything would cancel. Over here, atmospheres would cancel. Liters will cancel. 1 over 1 over mole is mole, so N equals moles. And I would take 1.5 divided by the 25.38, and we end up with 0.0591 moles. Okay. I personally, instead of doing it this way, I like to rearrange it first. So I would just take PV equals nRT, and I would rearrange it, divide both sides by RT, and I get N equals PV divided by RT, and then I just plug in and do one calculation instead of the two that we did. So it would be 1 atmosphere times 1.5 liters divided by 0.0821 atmospheres times liters divided by mole times Kelvin times by 309.15 Kelvin. And then just in one step I can say, okay, Kelvin's gone, liters gone, atmosphere's gone. I can plug it into my calculator, times to the top, divide, parentheses, times to the bottom, and I've got my answer. So that's the way I like to do it because it's all one step.
So when you're dividing it down, so the N would be 1.5 equals N mole?
N times this, and then I take and divide both sides by that.
So what happens to N on that side?
I just flipped it. N would have been on this side. It would have been here. And the mole would be on the other side, but it's the same thing, right?
Oh, okay.
Doesn't matter what side.
Measurements on the other side, except for the mole now?
Right.
Times it by 25.38 mole.
Dividing it by, yeah.
So that, because you're dividing it by the mole, then it's giving that one that measurement.
Yeah, basically I divided both sides by this number right here. Dividing this side by it gave me 1. Dividing this side by it gave me this number. Okay? All right, do we have another specific one that you would like to do? Or do you want me to just pick one? Charles' law, Gay-Lussac's, Dalton's, Graham's law. Yes? Graham's? Mm-hmm. Okay, Graham's is often done when you're talking about speed of a gas versus another gas. So if they say that N2 gas with respect to O2 is how fast relative, what's the relative rate is usually the words they use, the relative rate. So when I have something like that, I always identify as I first come along, this is going to be my A, this is going to be my B. So when I look at Graham's law, I say velocity of A divided by velocity of B equals the square root of the mass of B divided by the mass of A. Remember, they flip places. Okay, and that's Graham's law. So then I say, okay, then I'm going to go square root of B, which is oxygen, mass of oxygen, and it's O2, so 2 times 15.999 divided by the mass of A, which is nitrogen, which is 2 times 14.008 or 7. 7? Okay, the 2's here cancel out, right? I did that on purpose. So the less math I have to do, the better. And then I just put that in, take the square root of it, and I've got my answer. So if we do that really quickly on use the wrong one. Try this one. Did you get an answer? I'm being really slow.
So you do 15.99 divided by 14.007 and then square root that answer?
It depends on your calculator. Sometimes you have to hit the square root sign first and then put in the 15.99 divided by 14 in parentheses. So it just depends on your calculator. You should end up with 1.07. So basically that says the velocity of this is just barely faster than the velocity of oxygen. So velocity of nitrogen is just barely faster. Okay.
So if you were trying to find the mass and they give you velocity.
Okay, so they usually won't give you velocity. They'll say something like the relative rate of two gases is 0.073. The mass of one gas is 4.027. What is the mass of the second gas?
Oh, so usually they'll at least give you one mass.
Or they'll say the mass of, this gas is helium. What is the other gas?
So how would you?
Okay, so let's take this up. So we have it up a little bit higher. So again, we're still working with VA divided by VB equals square root of MB divided by MA. So as I come to it, I'm going to assume that this is A. Okay. And that's going to mess me up because I picked a light gas there. So let's pick a bigger gas here. Let's do xenon instead. Okay. So here what I would do is I plug in what I have. And that would be the relative rate, which is Z is this, is equal to the square root of an unknown divided by the mass of xenon, which is 131.29. Okay, first thing you want to do is square both sides. So if I square this side and I square that side, let's get rid of that, sorry, whoops. Just ignore that, okay. Then what I'm going to get on this side is 0.073. I'm going to get 0.005329 is equal to x divided by 131.29. And then you'll just times both sides by 131.29.
You have to square both sides.
Mm-hmm. You have to square both sides.
Just to get that one out.
Mm-hmm. And since I just did this off the top of my head, we're going to get a bogus answer. But the answer here would be 0.6996, which the closest one would be hydrogen, which is 1. Okay, so like I said, it's going to be a bogus answer because it's off, but that's just me. Okay, so then I would answer hydrogen. So I find the one that's closest.
Wait, so when we watch this on Canvas, do we hear you talk?
Mm-hmm.
Okay.
Yep. Okay, any others that you'd like to go over? Any other laws? Any other things? What's this?
Is that the ideal gas laws?
Toddler rules, kinetic theory. So what is Toddler rules?
The Toddler rules are inelastic.
Elastic collisions. Elastic collisions. Yes.
Oh,
Okay. So elastic collisions. Doesn't attract or repel. Doesn't take up space. Has something with temperature.
High temperature?
Kinetic energy is directly related to the temperature in Kelvin. What else? Now you're going to make me think. Okay. So, doesn't take up space. Random. Straight line motion was the other one we didn't do. Think of toddler. What does toddler do? Okay. So then we go to teenage rules. 3 things are different.
They have.
This is real gas. Inelastic collisions. Collisions are real.
They do attract.
Do attract and repel, and they take up space. So how do I get real gases to act more ideal? How do I get teenagers to act more ideal? High temperature, low pressure,
Big fall.
and I can choose who I hang with, nonpolar situations. That's the summer. Okay, so question.
Yeah, can you just go over endo and exothermic?
Endo and exothermic, the graphs or the what? So here's endothermic. I'm putting energy in, so I start with my reactants here. Here's my products. This point from here to here is my energy of activation, how much energy it takes to get the reaction started. From here to here is my change in heat or change in energy. And if it's positive, like it will be here, I had to put energy in, and this is endothermic. If I do another graph here, where I start and I end up below, here's my reactants, here's my products. Again, here's my energy of activation to the top of the curve, E of A. Here's my change in heat, which would be negative. And this top part right here is also known as the activated complex. It's where I can go either way. It's like setting at the top of a preface and I can go backwards if I don't have quite enough, or go forward if I just have a little tip.
So what would it mean if you were going, like what would happen to the substance if it was going backwards?
Then the reaction didn't happen.
So the reaction didn't work.
Right. I didn't have quite enough energy to make it over.
What's an example of endothermic? I don't get that.
Endothermic would be like I have an ice pack, I've hurt myself, and it's one of the ones you twist and the plastic between the two chemicals breaks and the chemicals start to mix and it feels cold to the touch. That's taking in heat from you. That's why it feels cold. So that's endothermic.
Heat from me.
Mm-hmm. Exothermic feels hot to us because it's giving off heat. So if we have the hot packs, that's exothermic.
So if we put an ice pack in a cold room that it couldn't absorb?
Depends on what temperature. They could be at the same temperature and then heat would not be transferred. In order for heat to be transferred, you've got to be at different temperatures. Okay, anything else you'd like to go over? The heat curve, the phase diagram.
I know.
Heat curve.
What is
Heat curve is when it go like this and you go, I'm heating a solid, I'm changing a solid to a liquid, I'm heating a liquid, changing a liquid to a gas, I'm heating a gas.
what happens when you heat a gas?
It gets really hot.
Oh, it doesn't.
You use pressure cookers at this point, and at this point use the equation Q equals mCp delta T. And Cp is different for all of those. At this point, where you're changing a solid into a liquid, you use Q is equal to heat of fusion times mass or times mole, depending on what your heat of fusion unit's in. Right here, you use Q is equal to heat of vaporization times mass or moles, depending on what you have.
You seem to be on the
Mm-hmm.
because I haven't seen it snap like it.
So you can take and say I had a popsicle in the freezer and I heated up and it melted, and then I heated up the liquid and it evaporated, and then I caught the steam up here. I would have 5 Qs that I would add together. I would do each one separate, and then I would add them together. Okay? Any others that you'd like to go over? Anything else in the pre-test that you'd like to go over? Because that graph is actually in your pretest. 42 through 49. You use that. Yes? 14, yes.
It's like, it starts with like Kelvin and Celsius. Do we have to change both, or since they want the answer Celsius?
Well, let's look at it. Okay, so let's read it. So on the first one, first thing you need to know, anytime you have Celsius, it's got to go to Kelvin, no matter what. When you're doing gas laws, when you're doing the mCp delta T, then it can stay in Celsius. Okay? All right, so here we have a gas is at a volume of 750 milliliters. And we have a temperature of 45 degrees Celsius. So I add 273.15 and you guys get that answer. Okay, and then it says at what degrees Celsius, so these are 1, I'm looking for T2. And it wants it in degrees C, so I know I'm going to have to convert it after. And would the gas have a volume half as large? So volume 2 is 750 milliliters divided by 2, which would be 375, right? Okay. All right. So at this point, I can say, okay, pressure's held constant, moles are held constant. So whose law is this? Pressure's held constant. It's Charles' law. So we're going to go V1 divided by T1 equals V2 divided by T2. And I'm looking for T2 down here on the bottom. So I'm going to do rearranging. If it bugs you to rearrange it, just put the numbers in and then solve. Doesn't matter which way you do it. I like to rearrange first, so I change places with volume 1 and T2 and then times through by T1. So I get T2 is equal to V2 times T1 divided by V1, and then I just plug in. Okay? You can do it step by step if you need to. You need to get T2 on the top and by itself. So plugging in, you go 375 milliliters times T1. We never did add that up, so 0.5. Okay. So 318.15 K divided by volume 2, or volume 1, which was 750 milliliters. Milliliters cancel. You should be able to times that through, get your answer. Once you've got your answer, you're going to subtract 273.15 and you'll get degrees Celsius. Okay, any other questions? Any other problems you'd like to go over that were in your pre-lab that you didn't understand how to get? Or pre-test, I should say, not pre-lab. Any other numbers? Yes?
42.
42. Okay, so all you have to do for 42, if it all at once is the melting point, is you look for the first flat area. And then you just read it right off the graph. So the first flat area is where you're going from a solid to a liquid, and that's the definition of a melting point, right? So the first flat one is melting point. The second flat one is your boiling point. Okay? Good questions. Any others?
I think, like, if you're teaching in class, you should record this. Like, I'd watch this.
Well, I do when we do tutorials. And I also record the class.
Oh, you record?
Yeah, they're up on Canvas, yeah. Yeah. They're through YouTube because I can't put all that. YouTube has unlimited, and I only have so much space on Canvas. So I link it through YouTube, but it is up there. Okay, any other questions you'd like to go over? That's a no, or are we just thinking? Yes?
We do 36.
36. Okay. Heat of fusion for zinc chloride is 40.4. Okay, stand up.
I
Pledge allegiance to the flag of the United States of America and to the republic for which it stands, one nation, under God, indivisible, with liberty and justice for all. Okay, we'll keep going.
The in-zone will be closed this week for
Program.
We'll be back in business next week. You need extra time to work on your homework? Come to our
And that's the heat of fusion.
A116 on Tuesdays at 7:30 a.m.
Okay.
and Wednesdays at 2:30. If you come to
And the melting point,
3 1-hour sessions, you can turn off
279 degrees C.
$5.
How much heat would be required to melt 4,892 grams?
From Hunter Svalberg, Bridget Brown, Chris
So all you have to do basically is just take and times those together,
Brendan Duffy, Dak Larson, Colby Wilkinson.
because your grams will go out and you'll get calories.
Come watch your nice wrestle.
Okay, so see how I pulled everything out and then I looked at it. Oh, what can cancel? That will cancel with that. That's how I did it. Okay, I always pull out.
Everyone is welcome to join us.
Okay,
How does having a social Friday?
all right, I'm going to shut this off now.